Material World today is looking at climate change and its effect of increasing turbulence and much quicker evolution. We'll join Quentin Cooper in just a moment. Now let's join Quentin Cooper for Material World.
Well, this is Gareth Mitchell, actually, but I do hope from here the show goes very smoothly today, although I must warn you, we are in for a bit more disruption. Scientific publishing is in the midst of a big old shake-up, and flying across the Atlantic is getting more turbulent. So, as we've been hearing, turbulent times in the world of scientific publishing, and also a bumpy ride ahead if you fly across the Atlantic, I'm afraid. The winds at high altitudes are already strengthening, so we are having increasingly bumpy flights on those trips across the Atlantic. And as if all that wasn't enough to have you spilling your drink, then brace yourself, because within about 40 years you'll be twice as likely to fly into turbulence. Not only that, the shaking will be greater, and that seatbelt sign will stay on for twice as long. Now, those worrying figures come from atmospheric scientist Dr. Paul Williams at the University of Reading and his colleagues, and they've been running computer models to predict conditions affecting aviation routes across the North Atlantic. Paul is currently at the European Union Geosciences General Assembly in Vienna, from where, just before we came on air, he told me about his findings and what causes turbulence.
Well, there are two important factors at work, and collectively they determine whether or not clear air turbulence will break out. The first one is the fact that the higher up in the atmosphere you go, the less dense the air gets. This is what scientists call stratification. The atmosphere is said to be stratified. And this is a stabilising influence. In other words, the stratification tends to inhibit or stop the production of turbulence. The second important effect is the fact that the higher up in the atmosphere you go, the faster the wind blows. So, for example, the wind speed in the jet stream can easily exceed 100 miles an hour. And this is what scientists call a wind shear. So it's the fact that the wind speed changes, increases with altitude. This has a destabilising influence. In other words, it tends to encourage the production of turbulence. So you've got these two factors, and they are in competition with each other, with the wind shear trying to produce turbulence and the stratification trying to stop it. So basically, whether or not turbulence breaks out depends on which of these two effects is stronger than the other.
And when we go on the plane and look at those moving maps, you often get a display that tells you that you're flying into a very strong headwind, or you might have a tailwind, so you get back to Heathrow half an hour early, only to then end up in a stack. But that's another story. But let's talk about how this is changing over time, because obviously we have climate change. What effect is that having on turbulence?
Well, most people, when you talk about climate change, they think about the fact that it is getting warmer in the lower part of the atmosphere where we live. But what is also the case is that climate change is changing the basic conditions in the atmosphere 10 kilometres above our heads where planes fly. And in particular, climate change is speeding up the jet stream winds. This is going to make the atmosphere more susceptible to the instability that causes clear air turbulence.
And you've managed to put some figures on all this. You've done some computer modelling, haven't you?
We have. In the study we're publishing this week in the journal Nature Climate Change, we've analysed supercomputer simulations of the atmospheric jet stream. And we focused on the North Atlantic Ocean, which is a very important region for aviation because there are 600 planes every day which cross the Atlantic. And what we found from these computer simulations is that the amount of airspace containing significant turbulence is likely, by the middle of this century, to double. And also that the average strength of turbulence we can expect to increase by between 10 and 40%. So that's an increase both in the average strength, but also in the frequency with which planes will encounter the turbulence.
Which I suppose means it's less likely that the planes can just fly around it. They can't divert necessarily because so much airspace is going to be affected.
Well, that's one of the possible implications. So as well as passengers expecting to encounter more bumpiness on flights, perhaps with the fasten your seatbelt sign switched on twice as long as it is today, if a pilot is taking off from Heathrow, say, and about to cross the Atlantic, the pilot will be staring in the face twice as much turbulence as would be the case today. So the pilot faces a choice then as to whether to grit their teeth and fly straight through it, or to try and go around it. And I think what we will see is that pilots will more and more decide to fly around these patches of turbulence when they become stronger. This could, of course, increase journey times and cause more delays at airports. and also, importantly, increase fuel consumption by the plane, which is, of course, the number one cost to airlines is buying the fuel. And so it's natural to expect that any increase in turbulence, if it does increase fuel consumption and increase costs to the airlines, that this extra cost could, of course, be passed on to passengers who may, by the middle of this century, be seeing increased ticket prices.
It astonishes me how soon this is going to happen according to your models. But let's think about ourselves on one of these flights compared to the experience that we have now, where I think I read on average you get 10 minutes of turbulence during a flight. How much will that increase by according to your calculations?
Well, yes, that figure's probably about right for a transatlantic flight. In 99% of airspace at any given time, the stabilising effect I talked about, the stratification, is strong enough to overcome the destabilising effect of the wind shear. And so 99% of airspace is basically free from turbulence at any one time. What we're seeing is that the jet stream is going to get stronger because of climate change, and that's going to strengthen the destabilising effect while not significantly changing the stabilising effect. And so climate change is really tipping the balance in favour of the production of turbulence.
How about its strength then? Is it going to be a minor inconvenience, maybe just spilling your coffee a little bit? Just how unpleasant will this turbulence be for passengers?
Well, in the study, we've looked at a specific kind of turbulence called moderate or greater turbulence. So there are scientific definitions of different categories of turbulence, and the one we've looked at is turbulence that is strong enough to bounce the plane up and down with a sort of g-force equivalent to about half of a g. So that's half the strength of gravity, in other words 5 metres per second squared. So this is quite significant turbulence. It certainly would require the pilot to put the fasten your seatbelt sign on. Certainly walking around on board the plane would be difficult. Serving food and drinks, very difficult. Certainly passengers would feel stresses against their seatbelt, maybe lifting out of the seat a little. So probably not strong enough to cause injuries, although some turbulence does cause injuries, and in fact hundreds of passengers and aircrew each year are injured. Sometimes fatally, I have to say, although very rarely. I think it's been about 15 years since someone was fatally injured because of an encounter with turbulence. But a typical injury might be a fractured skull. So if you're sitting down and your seatbelt is not fastened and you suddenly encounter some of this unexpected clear air turbulence, which the pilot can't see, by the way, from the cockpit, and the electronics on board the plane can't pick it up either, what typically happens is that you might lift out of your seat and strike your head against the top of the plane. So a fractured skull or fractured bones are typically what the injuries are. But I have to say the numbers are quite small compared to the number of people who fly every day.
So finally, I know you're looking at the North Atlantic here specifically in this study, but have you looked at other regions?
I have not yet looked at other regions. I think that's certainly what I'd like to do next, is to extend the study, because the jet stream in the Northern Hemisphere is, of course, not just confined to the North Atlantic sector. It goes all the way around the Northern Hemisphere and joins up at the other end, so it encircles the entire globe. And although I have not yet crunched the numbers on, for example, trans-Pacific airspace, it would be a reasonable hypothesis, I think, to imagine that the same sort of increases that we're predicting in this paper for transatlantic flights might also be seen for other parts of the globe.
Paul Williams of Reading University.